Hi everyone, I'm Khoshrav Doctor from the Laboratory for Perceptual Robotics at UMass Amherst, and I would like to discuss our work on learning to manipulate in open environments. We are inspired by Wolfgang Kohler's work on problem solving in chimpanzees. So in a similar study, we see a chimpanzee Vicky here, who's combining models of the objects, actions, and state transition functions in the environment. So with this cognitive support, Vicky can create novel solutions for acquiring this hanging banana by engaging the affordances of the objects in the environment. This presentation summarizes our work to implement a faithful computational model for this kind of problem solving. We've implemented an active belief planning architecture to produce Vicky-like behavior. So the components of this framework are robot and task independent, and tasks are addressed by condensing belief into state space partitions that satisfy the specifications. We start with a landscape of attractors that represent environmental stimuli. These aspects are denoted by X. Aspects support classifiers that recognize geometric properties of rigid bodies. A hierarchical base filter is then used to fuse the history of observations into a description of the latent states of entities like objects or rooms. And a belief space planner is then used to roll out future states in a belief MTP up to a bounded depth. This happens with the help of aspect transition graphs or ATGs that model probabilistic transitions between the aspects. This entire architecture we've demonstrated can be composed hierarchically to produce some interesting behavior. The role of the aspect transition graphs in this diagram is crucial. The ATGs influence all subsequent learning and planning, and it all depends on acquiring these models. Now I would like to talk about intrinsically motivated structure learning methods to construct the ATGs in a sample-efficient manner through exploratory interactions. The intrinsic motivator we use is the information gain over the distributions that the agent is building. We use the maximum reward or information gain left in the system to compare the IMSL approach to a random exploration strategy. IMSL quickly reduces the amount of missing information to converge with significantly fewer actions. We define alpha as the number of random actions that can be executed in the time it takes to plan and perform each intrinsically motivated action. To properly evaluate the expected impact, alpha considers both the total computation and execution time it takes to model the domain. Due to the lightweight aspect and ATG representations, IMSL outperforms random actions up to alpha equal to 1/20. To see the impact efficient forward transition models may have in robotic systems, we have some demonstrations of the architecture performing simple assembly tasks. The ATG, together with continuous error monitoring, provides a straightforward means of automatically improving the outcome of stochastic actions, like on the left. If a third-party adversary disturbs an intermediate state, this architecture can repair the disturbance seamlessly. And additionally, hierarchical planners can build interesting assemblies like this inverted pyramid that requires an eccentric mass distribution at the lower level to satisfy conditions between multiple objects at the higher level of the hierarchy. Thank you for listening, and please let me know if you have any questions.